In this video, we'll be graphing our logarithmic functions, and we'll discuss how logarithmic functions are actually inverse functions of exponential functions. So I've already got some chicken scratch written out up here, but let's focus on this stuff in purple first. Let me switch marker colors here. All right, so all the stuff that's written in the purple at the top of the page, for our exponential functions in the form y equals b to the power x, remember that we talked about how the domain is negative to positive infinity, range is 0 to infinity, y-intercept is 0, 1, and that they have a horizontal asymptote y equals 0. So over here in the right, we've got this pre-printed graph, and it's graphing y equals 2 to the power x versus the corresponding log function. So let's focus on the exponential first. Y equals 2 to the power x, underlined here in purple. And I wrote this XY table already. If you want, you can go into your graphing calculator and just confirm these numbers. So base 2 raised to the power x, and if you hit graph, there's the picture of your graph. If you hit trace, and then you type in your x values, for example, x equals -1, gives you y equals 0.5 or 1/2. If you type in x equals 2, that's where this 0.24 comes from. So these are the ordered pairs that are already plotted on the graph. So this guy, I'm just going to trace over it in purple, or attempt to. So that's our exponential function right there. And remember, we've got that horizontal asymptote, so I'm going to draw that as a dashed line also in purple. I'll erase this little arrow here. So that horizontal asymptote, I'm going to call it HA, is the equation y equals 0. Okay, so we all know this. This is review, hopefully. Let's go over to our blue guy, which is our logarithmic function. So over here, it also asks us to graph the function y equals log base 2 of x. And we'll find out in just a minute. We'll go through the derivation, but the logarithmic function is the inverse of the exponential function. So the logarithmic function is the inverse of that exponential function we just graphed. And remember, with inverse functions, it's a lot more complicated than this, but at the root, what I think of with inverses is switch x and y. So whenever I see inverse, I switch x and y. So for our exponential function, we had this xy table in purple. If we swap all of our ordered pairs, for example, that 2, 4 at the bottom of the exponential function now becomes 4, 2. I swapped my x and y values. The 1, 2 from the exponential becomes 2, 1 for the logarithmic. So if we switch all of our x, y values, that gets us this xy table over here. So these are our logarithmic function points. And that's what's graphed. The graph's already pre-printed. So I'll go ahead and retrace over it in blue. So this is our logarithmic function here. So let's take a look at its behavior. So first of all, the domain, remember the domain consists of our x values. So going from left to right, you can see that we have that asymptotic behavior where it kind of skates along this vertical y-axis. And the domain will go from 0, rounded parenthesis, up until positive infinity. So it's never going to equal 0. You can see that it skates along the axis just like our exponential function skates along that x-axis. So it's never going to equal 0. That's why we use that rounded parenthesis. The range, however, you can see that the function is going to go just down, down, down forever and ever and ever, and that the function is going to increase forever and ever and ever. So range is now negative to positive infinity. And just take a quick pause. Remember that with inverse functions, we're switching our x and y's. Remember that domain is your x values, y is your range values. If you look up at your exponential function, your domain was negative to positive infinity. Now that's your range for your logarithmic function. For your exponential function, your range was 0 to infinity. Now that's your domain for your logarithmic function. You're switching the x's and y's, including your domain and your range. All right, before we were talking about the y-intercept for our exponential function. Down here for our log function, we're saying what's the x-intercept? And we can see it's right here at 1, 0. Again, switching the x and y for our intercepts. And instead of having a horizontal asymptote, now we have a vertical asymptote. So I'll go ahead and draw this in red. My graph's getting a little, I'll do this yellow color. My graph's getting a little messy, but hopefully you guys can see this. So my vertical asymptote is going to run right along that vertical axis. So I'll call this a VA vertical asymptote. It's a vertical line. So I've got the vertical line x equals 0. Remember, your asymptotes are always stated in the form of an equation. So an asymptote isn't 0, it's x equals 0 in this case. All right, so how do we get to the fact that these are inverse equations? If you take a look at this box over here, it's got the process for how we go back and forth. If you start with your exponential function right here, so this is your exponential, right? F of x equals 2 to the power x. Rewrite that as y equals 2 to the power x. And then everything below this line, we're switching x and y and then solving for y to get our inverse function, right? So we switch x and y to rewrite this as x equals 2 to the power y. And then if you rewrite this in log form, log base 2 of x equals our exponent y. So y equals log base 2 of x, also known as f inverse of x equals log base 2 of x. So we start with an exponential, we get our log function as the inverse. All right, so down here, we're given a bunch of exponential functions and asked to rewrite these log function inverses. So for the first one, f of x equals 2 to the power x, we just found that f inverse of x is log base 2 of x. Over here, for f of x equals 3 to the power x, following that pattern, f inverse of x would be log base 3 of x. So we keep that same base. In the bottom left, f of x equals 10 raised to the power x. Now remember, when we're writing the inverse log function here, remember that base 10 means we're going to be using the common log notation, which means we're not going to write out a base. So the inverse function will just be log of x. So when we don't write a base, we know that that implies that the base is 10 for the common log. And for f of x equals base e to the power x, the inverse, we're going to use the natural logarithm, which is ln of x, and the natural log implies that there's a base e. All right, so let's look at some transformations from basic graphs, and we're going to use what we already know about transformations to decide where these graphs would move. So we're starting with our basic f of x equals log base 2 of x function. And I went in and filled in a few of these for the horizontal and vertical shifts because I think you guys are probably pretty good at these by now. So in A, g of x equals log base 2 of x plus 1. That's a vertical shift up 1 unit. For B, when we have the minus 1, that's going to produce a shift down 1 unit. In C, g of x equals log base 2 of x plus 1. That's going to produce a shift to the left 1 unit. Part D, the x minus 1, produces a shift to the right 1 unit. And then for E and F here, we have E, g of x equals negative log base 2 of x. This negative sign out in front of our function is basically changing the sign of all of our y values. And if we flip our y values from positive to negative or vice versa, that creates a reflection across the x-axis. And in part F, g of x equals log base 2 of negative x. Here we're changing the signs of our x values, which creates a reflection across our y-axis. Okay, so let's take a look at a few new graphs. I'll change my marker color here. Boom. All right, so for number 28, we want to graph g of x equals log base 2 of x minus 1. And up here in blue, I have the xy table from that original log base 2 of x function. So it's just the same table that we saw up here at the top of the page. I just copied it down here. All All right, so g of x equals log base 2 of x minus 1. This minus 1 is going to produce a vertical shift down 1 unit, right? So our x's will be unchanged. I'm going to copy down our x values, 1/2, 1, 2, and 4. But our y values, because y is our vertical movement, our y values are going to be subtracted 1, right? So -1 minus 1 gives me -2. 0 minus 1 gives me -1. 1 minus 1 gives me 0. And 2 minus 1 gives me 1. So let's go ahead and plot these. So I have 1/2 and -2, 1, -1, 2, 0, and then 4, 1. All right, so as I draw my log function, I always want to draw that kind of asymptotic behavior skating right along that vertical y-axis. Looking at my domain, it's unchanged, so it goes from 0 to positive infinity. Those are my x values. My y values, negative to positive infinity. My x-intercept is now going to be this guy, 2, 0. And as x approaches 0 from the right, remember that's what that little plus sign means, from the right. From the right. Okay, so as x approaches 0 from the right, f of x approaches negative infinity. So as we're getting closer and closer to 0 on our x-axis, our y-axis behavior, we can see that our function is just heading down forever and ever and ever. Our vertical asymptote is right here. I'm writing it with a dashed line. X equals 0. Remember, that entire equation is our vertical asymptote. All right, and for number 29, we want to graph log base 2 of x plus 1. Now that x plus 1 is going to create a shift to the left 1 unit. So our y values, our up and down, will stay the same. So copying from, again, this graph up here, our y values will stay the same, -1, 0, 1, and 2. Oops, let me scrub up a little bit, and 2, there we go. And then our x values, I'm going to subtract 1. So 1/2 minus 1 gives me -1/2. 1 minus 1 gives me 0. 2 minus 1 gives me 1. And 4 minus 1 gives me 3. So I'm just subtracting 1 from each of those values here to get my new x values. Let's go ahead and plot this. All right, so -1/2 and -1. Right about there, 0, 0, my origin, 1, 1, and then 3, 2. All right, so as I draw this, I want to have that asymptotic behavior again. All right, so you can see that my domain is actually different than it used to be. In all of these previous log function examples, we've had a domain from 0 to positive infinity, but now we have something different because we shifted our x values to the left one. Since we shifted our graph to the left one, our domain is now going to go from -1 up to infinity. Our range is still negative to positive infinity. Our x-intercept in this graph is now 0, 0. And now as x approaches -1 from the right, our function approaches negative infinity. And that means that our vertical asymptote has shifted over. In previous examples, it was x equals 0. Because of this horizontal shift, now we have the vertical asymptote x equals -1. So our vertical asymptote is x equals -1.